Now let us see PCl5, phosphorus pentachloride. Again, three aspects: structure, methods of preparation, and chemical reactions. Okay, first if you come to the structure. In chemical bonding, you spend considerable time on the structure of PCl5. Trigonal bipyramidal structure, one of the very important structures. Axial bonds, equatorial bonds. Axial bonds are longer than equatorial bonds. Two types of bond angles. You recall all of you? So, structure of PCl5, it is like this. Two axial bonds and three equatorial bonds. These two are axial and these three are equatorial. And hybridization of phosphorus is sp3d. Trigonal bipyramidal structure. And all of you try to recall why axial bonds are longer than equatorial bonds. And it's very simple. The bond angle between two equatorial chlorines is 120 degree, but the bond angle between one axial and one equatorial chlorines is 90. So, two equatorial chlorines are far away from each other when compared to one axial and one equatorial. That means the distance between two equatorial chlorines is greater than the distance between the axial chlorine and any of the equatorial chlorines. So, these two chlorines are far away from each other, so they are stable. And equatorial and axial chlorines are nearer to each other, so they repel each other. So repulsion between axial and equatorial chlorines is greater. So as a result, axial bonds elongate to increase the distance between equatorial chlorine and axial chlorine. So elongated. So bonds are longer. Axial bonds are longer than equatorial bonds. But all this, the structure of PCl5 is trigonal bipyramidal only in the gas phase. I think you all remember. If you see the solid state, then PCl5 solid, it is like PCl4 plus PCl6 minus. Now this is the solid state structure of PCl5 and this is the gas phase structure. Okay, now let us come to methods of preparation. And I already told you in the methods of preparation of PCl3, P4 plus Cl2. That combination gives PCl3 as well as PCl5, depending upon the conditions. In the excess of P4, we will get PCl3, and in the excess of Cl2, we will get PCl5. So, white phosphorus reacts with excess Cl2 and you will get PCl5. And under normal conditions, PCl5 is a solid. So, white phosphorus, which is a solid, white colored powder, reacts with excess dry chlorine gas to give PCl5 solid. Okay, another method of preparation of PCl3, and that method is also to some extent similar to the second method of preparation of PCl3. That is, you take that same white phosphorus and you treat this compound with SO2Cl2, not SOCl2. If you take up SOCl2 here, then you will get PCl3. But if you take SO2Cl2, I think you all remember its name, sulfuryl chloride. And this compound is obtained when H2SO4 is treated with PCl3. Okay. And you will get PCl5 plus SO2. Same product. But there is no H2Cl2 here. That is the only difference. In that case, we got two products of sulfur. here only one product. So there are two important methods of preparation of PCl5. One is with excess chlorine, reaction with excess chlorine, and another one is reaction with sulfuryl chloride. Now let me come to chemical reactions. And in chemical reactions also PCl5 is to large extent similar to PCl3. Now let us see. The first one, similar to PCl3, PCl5 also gives white fumes when kept in moist air. And to that extent it is similar. PCl3 gives white fumes, PCl5 gives white fumes, both give white fumes in moist air. But the difference is PCl5 hydrolyzes in two stages. In the first stage, it hydrolyzes partially to give POCl3 and HCl. POCl3 further reacts with water to give H3PO4 plus HCl. And obviously those white fumes are due to HCl. So PCl3 hydrolysis is complete in one step, but PCl5 hydrolysis is, it happens in two steps. So initially you will get POCl3, which is called as phosphorus chloride, sulfuryl chloride, SO2Cl2, and phosphorus chloride, POCl3. And second reaction, similar to PCl3, PCl5 also replaces OH group with Cl, wherever it is OH group, maybe in organic compounds or in inorganic compounds. So PCl5 replaces OH group with Cl. So you can take CH3COOH plus PCl5. You will get CH3COCl, acetyl chloride, plus POCl3 plus HCl. You can take ethyl alcohol plus PCl5. You will get ethyl chloride plus POCl3 plus HCl. You can take H2SO4, two OH groups are there in this. Both are replaced by chlorines. So SO2Cl2 plus POCl3 plus HCl. Sulfuryl chloride. Similarly, you take H2SO3, you treat it with PCl5, you will get thionyl chloride plus POCl3 plus HCl. Only thing is that the products are different here. POCl3 plus HCl. And in the case of PCl3, we always get H3PO3. Okay, and third reaction. PCl5, when heated, it sublimes. What is sublimation? Conversion of solid directly into gaseous state without the intervening liquid state. So PCl5 when heated, it sublimes. So directly converted into gas. But if you heat it more strongly, then PCl5 decomposes into PCl3 plus Cl2. And the last reaction of PCl5. PCl5 reacts with finely powdered metals. Suppose you take Ag plus PCl5 and you heat it. Heat this mixture. Ag is converted into AgCl and the other product is PCl3. And just you see this reaction, third reaction. PCl5 decomposes into PCl3 and Cl2. Here also it is decomposed because we are heating it. And whatever chlorine obtained, that reacts with silver and you will get AgCl. You can understand it like this. Similarly, if you take tin and you treat this compound with PCl5, you will get SnCl4 plus PCl3. Tin in the +4 oxidation state. Which oxidation state is more stable in the tin? In the case of tin, +2 or +4? It is +4. Inert pair effect is observed in lead. In the case of lead, the +2 is more stable than +4. But until tin, it is +4 only, which is more stable. So here it is SnCl4. So these are the four important reactions of PCl5. Hi students, now let me tell you about oxides of phosphorus. Next class of compounds of phosphorus, that is oxides. If you remember, in the general properties, when I told you about reaction of phosphorus with reaction of all group 15 elements with hydrogen, oxygen, nitrogen, metals and all that. So I told you that group 15 elements react with oxygen to form two different types of oxides, E2O3, E2O5, where E is a group 15 element. So if that is the case, then the oxides of phosphorus must be P2O3 and P2O5. But the actual formula of lower oxide of phosphorus, where phosphorus is in +3 oxidation state, is P4O6, not P2O3. Similarly, the higher oxide is P4O10, not P2O5. So two different oxides. So first one, P4O6, and second one, P4O10. What are the structures of these two compounds, how these compounds are prepared, and what are the chemical reactions of these compounds? Let me tell you. So first structure, P4O6 structure is like this. POP linkages. And here also one link, and here also one link. And each phosphorus has one lone pair. So it is basically P4, and between all phosphorus you insert oxygen. So you will get P4O6. And you please remember, all of you, there is no P2O3. Although P4O6 is generally written like this, but there is no P2O3. So wherever P2O3 is written, you just you take it as P4O6. If you come to P4O10, then its structure is to large extent similar to P4O6. Only thing is that here there are additional 4 oxygens, and those 4 oxygens are bound to phosphorus atoms. What is the hybridization of phosphorus here? 1 lone pair, 3 sigma bonds, sp3. And what is the hybridization of phosphorus here? 4 sigma bonds, 1 pi bond, so it is also sp3. But only thing is that there is no lone pair. And you see what type of a pi bond it is? P pi or P pi D pi? It is P pi D pi. 2p of this oxygen forming laterally overlapping with 3d of this phosphorus. So it is a P pi D pi bond. Of course, phosphorus cannot form P pi bond. There is no compound in which phosphorus is found to be forming that particular bond. Okay, so this is P4O6 and that is P4O10. Next point, we prepare P4O6 by treating white phosphorus with limited supply of oxygen. If it is excess, then you will get P4O10. P4 with excess oxygen will give you P4O10. But if you keep that oxygen as a limiting reagent, and not exactly as a limiting reagent, but in a limited supply, so then you will get P4O6. And best conditions for that is oxygen diluted with nitrogen. If you do that, then the major product is P4O6. Then in the presence of plenty of oxygen, you will get P4O10. And I told you, if you remember, whenever you study about an oxide, maybe it is in S block or P block or D block, the most important point, the basic point, most basic point regarding oxides is their nature, acidic or basic or amphoteric or neutral. And in our general discussion, at the beginning of this group 15, I already told you, E2O3 and E2O5 of nitrogen as well as phosphorus are acidic, while those of arsenic and antimony are amphoteric. Bismuth does not form pentoxide, bismuth only forms trioxide, and that is basic. So these two both are acidic, and if you dissolve this P4O6 in water, you will get H3PO3. And if you dissolve P4O10 in water, you will get H3PO4. Now, another important feature of this P4O10 is it is a very good dehydrating agent, removing water. It has a very high tendency to absorb water. So as a result, it removes water from the other compound. And do you remember recently we have seen that dehydrating nature of P4O10 in one of the reactions? Yes, during the preparation of N2O5. N2O5 is prepared from HNO3 by treating HNO3 with this dehydrating agent. Then you will get N2O5, dinitrogen pentoxide. So these are some important points of these two oxides. And now let me discuss about oxo acids of phosphorus. We have studied oxo acids of nitrogen also. Just you recall, all of you. We have 3 oxo acids of nitrogen: HNO2, nitrous acid; HNO3, nitric acid; and H2N2O2, hyponitrous acid. Okay, similarly we have oxo acids of phosphorus. I am discussing about 7 such acids. So first let me tell you one point before starting this topic. In all these 7 compounds which I am going to discuss, we have P double bond O, at least one. So each oxo acid of phosphorus has at least one P double bond O. And each oxo acid of phosphorus has at least one OH group. And some oxo acids, let me repeat, only some oxo acids have hydrogens directly attached to phosphorus. So P double bond O is common to all, OH attached to phosphorus is common to all. But in some cases, there are hydrogens which are directly attached to phosphorus. Those oxo acids in which hydrogen is directly attached to phosphorus, they have reducing property. They are reducing agents because of the presence of that hydrogen. Hydrogen directly attached to phosphorus. And all the oxo acids have OH group. So all of them are acids because H attached to O is ionizable. A base can replace it. So all oxo acids are basically acids, no exception. But some of them are reducing agents also, apart from being acidic in nature. So just observe this property carefully. So let me start listing these 7 oxo acids of phosphorus. Okay, in this the first one is hypophosphorus acid, which is also called as phosphinic acid. Try to remember the names, all of you. Hypophosphorus, which is also called as phosphinic. Formula H3PO2. Structure: 1 P double bond O, 2 hydrogens directly attached to phosphorus, and 1 OH. Hybridization of phosphorus is sp3. And you see what type of a pi bond it is? P pi, D pi, 2P and 3D. And you see whether it is a reducing agent or not? Yes, because of the presence of these 2 hydrogens, it is reducing in nature. and its basicity, the maximum n factor. Basicity is the maximum number of H plus ions that are replaceable. So basicity is 1 only. These hydrogens are not replaceable, they are not replaced by a base. Of course they are replaced in a redox reaction, that is a different matter. And seeing the redox reaction, we don't define basicity. Basicity is related to acid-base reaction. So when you treat this compound with excess base, lot of base, the maximum hydrogens that you can replace is only 1. And none of these two is replaced. So basicity is 1. And how do you prepare this compound? We have already seen that reaction. You take white phosphorus, you treat this with NaOH in the presence of water, and in a disproportionation reaction, you will get phosphine plus NaH2PO2. NaH2PO2 is nothing but the salt of this acid, hypophosphorus acid. So now you take this NaH2PO2 and you treat it with any acid like H2SO4. So you will get H3PO2 plus Na2SO4 or NaHSO4, sodium sulfate or sodium bisulfate. So this is how hypophosphorus acid is prepared. You see just the important points of that acid: structure, basicity, hybridization, whether it is reducing or not, and method of preparation. Now second one, second oxo acid, that is orthophosphorus acid, which is also called as phosphonic acid. And its formula is H3PO3. And in our previous discussion we have seen this actually directly like this. PCl3 gives white fumes in moist air. You recall, all of you, the product is this one only. PCl3 reacts with many compounds having OH group, replacing that OH group with Cl, and in that reaction also this is the product. Okay, H3PO3, and the structure P double bond O, 2 OH groups and 1 H. So decide whether it is reducing or not. Yes, it has one such hydrogen which is not replaced by a base, but because of which this compound acquires reducing nature. So basicity of this compound is 2. The maximum hydrogens that are replaceable by a base. Okay, and this compound is prepared. You already have seen this. You take P4O6, the lower oxide of phosphorus, and just you treat it with water. You will get H3PO3. Now that is how this orthophosphorus acid is prepared. Now third one, it is pyrophosphorus acid. And please remember, all of you, wherever you see this prefix pyro means heating. You heat something, water is eliminated, and the resultant compound will get that prefix pyro. Pyrosulfuric acid, pyrophosphoric acid, pyrosilicates, everywhere. So now here, you take 2 molecules of this acid, remove water, and the resultant compound is pyrophosphorus acid. So 2 molecules, H6 minus 2, H4, P2 remains as P2, O3, O6, if you take 2 molecules and remove 1 oxygen, because we remove 1 water, so O5. And the structure of this acid is P double bond O, P double bond O, OH, H, OH. Now this is the structure of this pyrophosphorus acid. It is something like this. You take 2 molecules of this P double bond OH, 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 another such molecule P double bond H, OH. Now you remove water. You will get that compound. And what is the basicity of this acid? Obviously it is 2. And now you see whether it is reducing or not. Yes, because of the presence of these 2 hydrogens. And now you prepare this acid by heating orthophosphorus acid. H4P2O5 plus water. Or else you can also prepare this by treating that H3PO3 with PCl3. PCl3 is a kind of dehydrating agent. So here also you will get H4P2O5 plus H3PO3 plus HCl. Okay, if you come to the next acid, that is hypophosphoric acid. And it is H4P2O6, hypophosphoric acid. And its structure is P double bond O, P double bond O, OH, H, O, this is also OH, OH and OH. And what is the basicity of this compound? Basicity is 4. And see, in this compound there is PP bond, and here we don't have such a bond, and here we don't have pH bond. So this compound is not reducing in nature. This is only acid. But these 3 oxo acids are acids as well as reducing agents. Okay. Now this compound is prepared by heating red phosphorus with an alkali. When this mixture is heated, you will get this compound. So these are the first 4 important oxo acids of phosphorus. All of you see, differentiate whether it is an acid or reducing agent or both, methods of preparation and what is the basicity and structure. And you see, in all cases the phosphorus is sp3 everywhere. Here also both phosphorus atoms are sp3. Here also sp3. And all the pi bonds are p pi d pi bonds. Let me continue to the oxo acids. Now let me tell you the rest of the 3 acids. The 5th one is H3PO4, orthophosphoric acid. This is the most important oxo acids of phosphorus, and you frequently come across this. The formula H3PO4, and the structure P double bond O, OH, OH and OH. There is no hydrogen attached to phosphorus. Basicity is 3. That means it can react maximum with 3 moles of NaOH. So 3 replaceable hydrogens. And you can prepare this by treating the higher oxide of phosphorus, P4O10, with water. So H3PO4, orthophosphoric acid. All of you please remember one thing. This is generally called as phosphoric acid. Generally that prefix is omitted. So its actual name is orthophosphoric acid, which is more famous by simply phosphoric acid. Okay, and 6th one, pyrophosphoric acid. And again you see pyro. You take 2 molecules of this, you remove water, you will get pyrophosphoric acid. So H4, 6 minus 2, P2, 8 minus 1, O7. 2 molecules of H3PO4, or you can say 2 moles of H3PO4, remove 1 mole of water, you will get pyrophosphoric acid, H4P2O7. And its structure is P double bond O, O P double bond O, OH, OH, OH and OH. And its basicity is 4. and it is not a reducing agent. You don't have a single hydrogen attached to phosphorus, directly attached to phosphorus. And it is prepared by taking orthophosphoric acid, and you either heat it or you add any dehydrating agent like PCl3. So then you will get H4P2O7, pyrophosphoric acid. Now the last one is metaphosphoric acid. Actually, metaphosphoric acid formula is HPO3 taken n times, and n value is 3, 4, so on. Minimum value of n is 3, it can be 4, 5, so on. When it is 3, it is called as trimetaphosphoric acid. When it is 4, it is called as a tetrametaphosphoric acid. So like that, penta, hexa. And one more thing. When I explained this particular acid, I told you that you take 2 molecules of this and remove water, you will get this. Now, suppose if you talk about trimetaphosphoric acid, you take 3 molecules of this, remove 3 water molecules, and you will get trimetaphosphoric acid, and its structure is POP, and each phosphorus is bound to one oxygen and another OH. So double bond OH, double bond and OH. Now you have taken 3 H3PO4. From the first 2 remove water, from the next 2 remove water, then from the first and third remove water, cyclic. So trimetaphosphoric acid, HPO3 taken 3 times. And what is the basicity of this acid? That is 1, 2, 3. So you can say in metaphosphoric acid, the basicity is nothing but equal to N, because number of OH groups are equal to N. So basicity is 3. And you can prepare this acid by taking H3PO3, and you heat this H3PO3 with Br2 in a sealed tube. Then you will get HPO3 taken n times plus HBr. That is how we prepare the metaphosphoric acid. Okay, actually HPO3 taken n times we have already seen. And let me tell you where we have seen this. You take HNO3, you treat this compound with P4O10, and you will get N2O5, dinitrogen pentoxide. And just you recall, all of you, what is the product of phosphorus you obtain here? Nothing but HPO3 taken n times. But at that time, I have written metaphosphoric acid like that only. But it is actually HPO3 taken n times. So, whenever P4O10 acts as a dehydrating agent, you will get this compound. The product is this compound. So, P4O10 absorbs water, converts into this compound. If there is more water, you will get this compound. If there is more water, you will get this compound. And you take this, remove some amount of water, you will get this. Remove more amount of water, you will get this. And remove the water exhaustively, you will get P4O10. So go on adding water, go on removing water, opposite direction. Okay, and 2 other reactions actually which we have seen about these oxo acids in our previous discussion. You recall all of you, H3PO2. What is the name of that compound? Hypophosphorus acid. You warm it, you heat it, so you will get H3PO4 plus phosphine, PH3. Now, similarly, you have H3PO3, its name is hypophosphorus acid. You heat it, you will get H3PO4 plus phosphine. All of you recall? In the topic oxidation states, we have discussed that. Intermediate oxidation states of phosphorus, like +1, +3, they tend to disproportionate in both acidic and basic medium. We have discussed that, do you remember? So these are some of the reactions of oxo acids of phosphorus which we have seen in our previous discussion. Okay, now this is the sixth acid, this is the fifth, sixth and seventh. So this is all about oxo acids of phosphorus.